I'm Jonathan Eckstein. You probably know that. Okay. Anyway, I'd like to thank, so this is part of DIMAC's special focus on bridging continuous and discrete optimization. And it says on a later slide, it's a whole sequence of workshops, and this is the first one. Okay. And it was organized by DIMAC, of course, and Simons Institute, and the funding comes from NSF. The organizing committee is me, Farid Alizadeh, who's also from Rutgers and is taking his son to the LSAT right now, but he'll be here later today. And John Paul Watson from Sandia, who's there, and Dave Woodruff, okay, from UC Davis. I'd like to thank the DIMAC folks who put in a lot of work to set this up. Tammy Carpenter, who's the lead person. Linda Casals, who does all the scheduling and the website stuff. Nicole Clark. Walter Morris is their systems person. And all the speakers who agreed to attend, including one who came on very short notice because we had a slot open up due to cancellations. A few people who I thought were going to be here are not going to be here. Xiaomin Wang, Dimec Davis both had like serious personal issues. And actually we just heard also the very last speaker on the schedule, Gabe Hackabile, canceled this morning. Okay, but we'll make a little adjustment. We'll probably be able to get out of here a little earlier on Wednesday. But so there'll probably be a slight additional change to the schedule for Wednesday. Okay. You don't have to do this before you give your talk or anything, but you have to. But they want you to fill out this video release form, or you can formally refuse to release, but you need to tell them what you want to do. So this conference basically started with an email in December 2016 from Tammy to Farid, and then Farid to me. And we put together like a one-page proposal that went into this bigger proposal, NSF, in January 2017. We got funded in September, and we're the first workshop. Okay? So the idea of the workshop is to bring together, like some of you are theoreticians of operator splitting and ADMM and wonderful things like that, and then also some practitioners who are using this type of methodology to solve real-world problems, particularly ones that those algorithms weren't intended for, such as ones with discrete variables or non-convex functions or something like that. So, and some of the people doing that, so this community has arisen of people using this progressive hedging algorithm to solve stochastic programs, which is a special case of operator splitting and ADMM, but I think many of the people who are using it maybe didn't know that in the beginning. So I was trying to bring together people from those two communities. And please stick around for a whole workshop if possible. It was going to be at a different time, but what has ended up being the last talk, you will see a guy from the astronomy department at Princeton picking apart overlapping images of distant galaxies using an operator splitting method. So that should be fun. Okay. So let's see. That's basically the welcome. So I'm actually like 2 minutes early to start the talk, but whatever. Okay. So.
You use the extra 2 minutes.
Yeah, I can definitely use it. Okay. Actually, my normal pace is 1 minute per slide, so this I will just make it then, supposedly. Okay. So the idea of this talk, Patrick Johnstone, who's a postdoc who's been working with me for the last year and will work for me for another year, he's going to talk about some of the recent things I've done. What I thought I would do is give a talk that kind of tries to get people on the same page. Like there may be operator splitting people that don't know progressive hedging, and maybe progressive hedging people don't know operator splitting. And so I thought I'd just kind of give everyone some context, and so hopefully we'll make more of what comes later understandable to more people. And I'll throw in a few like historical nuggets, at least from my perspective. Okay, so the first part is like I got involved in this stuff in like the late 80s, okay? And it was not very well known then. So my advisor was Dmitry Bertsikas, and when I started working with him, he had me work on these pre-flow push. He was very into these pre-flow push min-cost network flow algorithms. And it got a little uncomfortable because there was a big priority fight going on about these algorithms, which basically later it turns out no one ever uses, but that's a different topic. Okay. But it was getting kind of nasty, and I was sort of in the middle of it. And I had also done an implementation and discovered the algorithms as originally described were really slow. And you could speed them up, but when you sped them up, you were basically turning it into the Hungarian algorithm, which was already well known. So it was kind of, anyway. So I was getting kind of disgusted with this line of research, and so like in early 1988, I went to my advisor and says, I don't really want to work on this. And here's an idea of something else I want to work on. And I had some idea for doing the same thing with network flow, but using like some quadratic perturbations and stuff. And I just went away for a week. And I came back, and he said, John, I read your write-up. Your ideas are not very good. I gave this in a talk in his honor at MIT, and he said, did I really say that? But he did say that. I remember, okay? But they remind me of a topic that I'm wondering about, okay? And the topic was, what is the relationship between the standard augmented Lagrangian method, the proximal point algorithm, the alternating direction method of multipliers, okay? So I knew about the augmented Lagrangian method. I had no idea at that time what proximal point algorithm was and what alternating direction method multipliers was, but he gave me some papers to read. Okay? And the situation that existed at that time, so augmented Lagrangian method had been developed in the 70s. Okay? And in 1976, Rockefeller showed that in the convex case, it is an application of Martinet's proximal minimization algorithm to the dual. Okay? And then there was a paper in French in 1975 by Glavinsky and Morocco that actually had the ADMM in it, but only as a heuristic. Okay? So they basically said they were using augmented Lagrangian. They were using an alternating minimization method to solve the subproblem, and they just discovered by experimentation that the whole thing worked the fastest if they just did one block minimization, other block minimization, didn't check at all if they had done anything to really minimize the subproblem, just go. So they found empirically that worked okay, but they had no theory about it. Okay? And so in 1988, when Dmitry handed me the first paper on this stuff that I saw, it was a very obscure method in the optimization community, and it continued to be so for at least 15 years. Okay? Between 15 and 20 years, things started to change. Okay? Now, in 1983, this edited volume, which edited by Fortin and Glavinsky, came out. Okay? And it had two very important papers in it. So the first one was by Fortin and Glavinsky, and it was an analysis, convergence analysis of the ADMM using variational inequalities. Okay? But it showed that what Glavinsky had been doing earlier did actually converge. Okay? And then there was this alternative analysis by Gabay, which was the one that really grabbed me, that showed that it was actually a dual application of this thing called Douglas-Ratchford splitting, which had just been proposed only a few years earlier by Leon and Mercier. Okay? Which is, it's a splitting method for monotone operators, and most of you here know what that is, but for the progressive hedging people, I will explain that in a second. And now, Douglas-Ratchford method, which was proposed way back, maybe 50s even, when it was originally proposed, it was just for solving the heat equation on a two-dimensional grid. Okay? And it was never proposed by Douglas and Ratchford as anything more than something for solving linear equations. So Leon Mercier generalized it massively to nonlinear operators that could be set valued and all sorts of stuff, okay? So we always call it Douglas Ratchford because that's what they called it, but we should probably call it Leon Mercier. And so these two analyses in this 1983 volume are basically the foundation of every analysis of ADMM that's come afterwards, okay? And they're very similar, and it took me a while to realize that they're not identical, okay? All right, so this is technical segment 1, and if you're an operator splitting person, this is a good time to like check email or whatever else you want to do, because it's really, you're going to know it very well. So, all right, so this is mostly for the progressive hedging people, but so if you can, let's just take a convex function, and the convex function maybe could be infinity in places, so it has kind of constraints embedded in it. So there's this notion of a subgradient, okay? So the subgradient at a particular point is just the set of all slopes of linear underestimators of the function at that point, or affine underestimators of the function at that point. And so you can consider it this thing where you give it a point and it gives you the set of all subgradients at that point. It's like a point-to-set map, okay? And they have this, there's a standard property of monotonicity, which is basically if y is a subgradient at x and y prime is a subgradient at x prime, then the inner product of the differences is non-negative. And it's actually extremely easy to prove that in this case, because it's just like, okay, I take an underestimate of this function, I go to this other point, okay, and then I take another underestimate, I basically have to land up underneath where I was, and that's the proof, okay? Okay, and this is called being, when you have a point-to-set map with this property, it's called a monotone operator. And not all monotone operators are subgradients of things, okay? And it's called monotonicity, okay, because you can, it's sort of a generalization of a function in R1 being non-decreasing. It basically says, if you take the graph of this point-to-set map, okay, so here's, like here it's a vertical place, that's where it's multiple valued. It just says, okay, in R1 it just says if I connect any 2 points on this graph, I can't have a negative slope. Okay, that's all it is. Okay, and that leads immediately to this thing I call the representation lemma, which just says, okay, if I have any point t, I just pick a constant c. It can be 1. Okay, so some positive constant c, and every point in the space can be expressed in at most one way as x plus cy, where y is a subgradient of the, or y is in the image of the operator at x. Okay? And here's a picture proof of it, which is very simple. It's basically, okay, if I just graph the line or plane of x plus cy equals constant, I get this thing that has negative slope. Okay? And so I can't intersect this set in more than one place, because if I did, I would be connecting 2 points on that graph with something with negative slope. Okay? And in higher dimension or infinite dimension, it's the same idea. The proof is like 2 lines long. Okay? That basically, if you have 2 points that both satisfy, two things like this that are equal, basically you have to have a negative non-positive inner product between these two differences, and that the only possibility then is 0, because if you have monotonicity. Okay? Now, a step beyond that is what's called Minty's theorem, and that says, okay, if I have an operator which is what's called maximal, or Bausch and Combats call it maximally monotone, if I have one of those, okay, then which means that I can't add any points to that graph without destroying the monotonicity property, okay? Then at most one way becomes exactly one way. That every point in the space can be decomposed in this way, like x plus y, where y is in t of x, okay? So I think of that as just a generalization of, if you have a linear subspace, every point can be decomposed into the sum of a point in the subspace and a point in the orthogonal complement. This is a generalization of that. Any maximal monotone operator gives you a decomposition of every point in the space in this way. Okay? Now, for example, if a convex function is lower semi-continuous, which is a very, very weak condition, okay? So any non-disgusting function is basically lower semi-continuous, then it's going to, it will, then the graph will be maximal, and you're fine, okay? So this, the operator, okay? Okay, so here is, for the progressive hedging people, here's a simplified way to think. I'll lead you into this whole operator splitting idea. So I'm going to define this. So I'll take a constant C and an operator T, and I'll define this reflection map as follows. I give the map a T. Okay? I know I can, if I have one of these maximal monotone operators, I know I can express it uniquely this way, okay, as x plus cy, where y is in T of x. But and then what I return is x minus cy. Okay? So this, if T, if you were doing this thing where you're decomposing into a subspace and orthogonal complement, this would be reflecting through the subspace. Okay? It turns out this map is non-expansive. Okay? It's Lipschitz continuous with modulus 1. Okay? And it's defined everywhere if T is maximal, and its fixed points are what are called the zeros or roots of the operator, the place where 0 is in the image, which if it were a subgradient, those are minimizers of the function. Okay? The proof is really simple. Okay? You just say, okay, I take the difference of these 2 points and expand it out. I take the difference of these 2 points and expand it out. And the difference between them is twice this term. Okay? So this is the difference of reflections. That's the difference of the arguments. So the difference of reflections equal this. It's 4c times this inner product less than this guy. Okay? And this thing cannot be negative, so there has to be less than or equal to. Not expansive. Okay? Done. And then the fixed point property is basically, well, if it's a fixed point, x plus cy must equal x minus cy, which means y is equal to 0, and then x is equal to t, and you're done. Okay? So it's very simple. Okay? So this suggests, okay, so maybe we could have an algorithm based on this. Okay? We have some, say I want to find a root, 0 of this operator. I have some non-expansive map. Okay? So I could just try it, and its fixed points are the points I want. So I could just try iterating it. Okay? But okay, the Lipschitz constant is 1. Okay? It's not less. If it was strictly less than 1, we would just converge linearly. Okay? But it's 1. So we could just orbit, just like never get any farther, but never get any closer. Okay? And the amazing thing, so this was first discovered in 1955, is if you're trying to find a fixed point of a mapping with Lipschitz constant 1, you can still just iterate it. What you do is you blend in a little bit of the identity, and it works. So this was, it's also, it's called the Krasnozelsky-Mann iteration. I think Krasnozelsky probably published it first. But the blending factor here, for historical reasons, I'm calling it, I'm having it be between 0 and 2 instead of 0, and then I divide by. Okay? But for example, if I set this blending factor to be 1, I'm just iterating half of the identity plus half of this reflection map. And that will converge. In infinite dimension weakly, but okay. And this map is called the Prox map. Okay? And you can think about it in the following way. I give it a t. It decomposes it to x plus cy, where y is in T of x. But instead of x minus cy, it just returns x. And it's called the resolvent. Okay? And Rockefeller's proximal point algorithm is basically just to iterate this map. Okay? Except you're allowed to vary the c as you go. Just can't let it go to 0. Okay? And that can be generalized in many ways. You can put in inexact computations as long as you're not too far off. You can vary the mixing factors as you go, et cetera. Okay? So the question is, all right, that's fine, but is that anything you could actually do? And the problem is that this Prox map is not always that easy to compute. Okay? So for a general function, the way you compute that Prox map is you minimize the function plus a quadratic perturbation, okay? Which is probably just as hard as the original function. So it's, and this is This is a calculation in Martinet's earlier algorithm, I believe. But Rockefeller in 1976 had this insight. It said when this f comes from the dual of some optimization problem with a constraint, computing this is not really any harder than computing the original dual function. And he also found that the augmented Lagrangian method is basically just doing this iteration on the dual. Okay. So now, this is kind of getting kind of long-winded, and I know a lot of you know this already, but I want to talk about operator splitting. So the idea of operator splitting, okay, is that suppose we want to minimize the sum of two, or we want to find a zero of the root of two operators. So that basically means some x where there's a y is in the image of one and minus y is in the image of the other, so they cancel out. Okay? It's equivalent to, say, minimizing the sum of two non-smooth functions that are convex. Okay? And suppose I can do these prox or reflection operations on the individual operators, but I can't do it. It's too hard to do on this guy. So there's some special structure there. And the idea is, can you converge to a minimizer or sum only through evaluations of these things? And the answer is yes. Okay? And the kind of canonical way to do it is okay, I have one non-expansive map which goes with this operator. I have another one that goes with the second operator. Okay? And so it's a simple observation. If I take two non-expansive maps and compose them, I get another non-expansive map, right? And it turns out in this case it's convenient, okay, because the fixed points of that map turn out to have exactly this form. Like they're x plus cy, where y is in T2 of x and minus y is in T1 of x. So that if you have a point like that, you have a solution. Okay? And the proof of that is pretty straightforward, actually. So it's kind of like two equations in two unknowns. Okay? So we could just try. So hey, we have a non-expansive map. Its fixed points are basically give us the solution to our problem. So let's just iterate it. Okay? Well, it's non-expansive. The Lipschitz constant might be 1. So we have to iterate it blended with the identity a little bit. Okay, a little bit or a lot. Okay? And the case where you blend it half and half with the identity, that's Douglas-Ratchford splitting. If you don't blend it at all with the identity, it's called Piesman-Ratchford splitting. But then in general, it doesn't converge. It will converges if you have some additional assumptions. Okay? There are other things like this, like there's forward, backward, where you basically just take just evaluate the operator, don't do one of these proc steps, then do a proc step on the other operator, things forward, backward, forward, projective splitting. There's some other things you can do like this, but this is the basic idea. Okay? So now we get to this thing called the ADMM. Okay? So I have two functions, f and g, on different spaces and a linear map between them, and I want to solve this problem. Okay, so I write it this way. This is the Lagrangian. So basically the idea is if I take the dual of this thing, if I take the dual function of this, it splits nicely into two functions. It's like a sum of two different functions of the Lagrange multiplier. And so what you can do, they're concave. I just flip them around so they're convex. And it turns out, so what Gabay figured out in 1983 is if you take the problem of minimizing the sum of those two pieces of the dual function and you apply that Douglas-Ratchford splitting idea to it, out comes this algorithm, which is called the alternating direction method of multipliers, where you just minimize the augmented Lagrangian with respect to one block of variables. Then with the other block of variables, then you multiply or update this. So this is exactly the thing that Glavinsky and Morocco found heuristically in 1975. But then now they know it converges. Okay. There's an interesting thing. There's also this Fortin-Glavinsky proof of the ADMM, which originally I thought, oh, this is just a more complicated version of the Gabay proof, but it turns out it isn't. It's really based on if you write the Lagrangian and split it into two pieces. And then it turns out Lagrangians also have subgradients, and those in a certain sense, and those subgradients are also monotone. And you can use that property to get the following. This is called phasor monotonicity. We're always getting closer to the set of solutions, or at least you're not getting farther from them. And it turns out you're getting closer. Basically, the fixed points of the algorithm look like this. They look like an optimal Lagrange multiplier, optimal z variables, and this c scaling factor. And you're always getting, you basically have phasor monotonicity always being drawn into points like this. The weird thing is, the Gabay-Lyon-Mercier analysis, it looks almost the same, except as an ordered pair, you have a sum here. So it's kind of in a lower dimension. And it turns out it's not exactly, it looks really similar, but it's not exactly the same. And for example, if you include over-relaxation, like having that mix in the Gabay form, having a mixing factor, it's not always a half, okay? You actually get slightly different things with these two analyses. So it's like two families of very similar algorithms, and they intersect. They're identical when you have rho equal 1, when the mixing factor is a half, but they're actually slightly different otherwise. I mean, they resemble one another, but they're not exactly the same. OK, now I have like 9 minutes to go through. So that's the end for the that's the end of the background. For those who might not have had it. Now I want to talk about progressive hedging. Now this is an algorithm that it's a big time application of operator splitting, but a lot of sort of math people in the operator splitting world don't necessarily know this algorithm, so I'm going to introduce it to you. Okay, so what I'm going to do, I'm going to take my set of variables and I'm going to chop it into p blocks. Okay, and on each of those p blocks I'm going to have some convex function. And then I'm going to have another map, a linear map on each block. And I'm going to look at the following problem, that I want to minimize the sum of all these functions. This is a separable sum here. All these xi's are different subvectors. And then I apply a linear map, basically, to each of these vectors. And I get another vector in this product space. And I say it has to be in some arbitrary subspace. So this thing, this V, is the only thing that links everyone together. Okay, and if you apply the ADMM to this setup, it means f is this function, g is a function where I just feed it an argument, and if the argument's in this subspace v, it says 0. If it's not in the argument v, it says infinity. Okay, and then I have a certain linear operator here, this m. Okay, and now. So with this setup, that problem on the last slide is just this ADMM type of format. Okay? You want to minimize f of x plus g of mx. Okay? And if you just put that into ADMM and turn the crank, you get the following algorithm where I minimize each of these functions f, but with a certain quadratic perturbation. Okay? And then I apply the linear map to what I get, and I project that onto the subspace. This is actually minimizing the function g. That gives me a z, and then I do a multiplier update. Now, just as an aside, anytime you're doing ADMM with a function like this, you're applying this thing called Spingarn's method of partial inverses, which you can look at as a special case of Douglas-Ratcher splitting. Okay? So now, what does all that have to do with stochastic programming? Well, here is some tree, okay, with, say, S stages. Okay, maybe this pointer isn't the greatest. I'll just go up here. Okay, yes, S stages. I have P last stage scenarios. Okay, and so here's what I'm going to do. I'm going to take the decision variables at each stage, and I'm going to replicate them. Okay, so at the root, I'm going to have P copies. Okay, I'm actually going to have P copies at every stage. Okay. And the z's that's the x variables. The z's are the same, except that I just don't have the last stage in there. Okay, good. Okay. And now I'm going to formulate a linear subspace that says all those first stage variables have to be the same. Okay. Second stage variables that correspond to the same node in that tree have to be the same, et cetera. It's called it's one of the worst words in supposed English, non-anticipativity. Okay? All right. So anyway, so if I now define a function, fi, so hi is going to be the cost function for scenario I, supposing I could see the entire future. Okay? And infinity if I do something infeasible. Just weight that by the probability of the scenario. That's f. M is just the matrix that drops the last stage variables from a scenario. And the stochastic program is exactly in this form that we just said. Okay? And then if you apply ADMM to it, you get the following thing, where you take every scenario individually, like you could see the entire future, and minimize it with a quadratic cost perturbation. Okay? Then all those variables that are supposed to be the same, to be non-anticipative, not to see the future, are averaged. And then I do a multiplier update on that constraint that everything has to be the same if you can't see the future, and I loop. Okay? Now this isn't exactly what Rockefeller and Wetz proposed, because they used a probability-weighted inner product, which basically gives you the same algorithm, except now the averages are probability-weighted. Okay. So, all right, so closing. Almost everything I talked about was known by 1990. Okay, not necessarily by the same people, but everything was known by 1990. Okay, and I did this theory in my dissertation. I thought this is cool, and I tried some applications, but they were to standard like OR type optimization problems like min cost flow, and it didn't work very well. And so I went and did other things. And progressive hedging didn't really catch on for a while. But now you go forward 20 years, and people found out ADMM really works nicely for L1 regularized quadratic problems, and there's this nice PySP system for modeling quadratic stochastic programs that has a nice Python modeling language and a good implementation of progressive hedging. So now these algorithms are kind of popular again. But there's some issues, like one thing that the progressive hedging people really like to do is they often have real problems that have discrete variables. And it's very easy to just heuristically apply progressive hedging to problems like that. And it's much more tractable than, say, forming a giant LP and just feeding it to Garobi and crossing your fingers, okay? Or giant MIP and crossing your fingers. But the theory doesn't really tell you much what happened there. But it turns out some work's been done recently. So can doing something like that be more than heuristic? And you'll see in Jim Ludke's talk it can be. It can give you some nice Lagrangian bounds. We can apply these ideas in other contexts as well. Non-convexity is another important area. So what happens when the problem's non-convex? Can ADMM, things like that, be more than heuristic? So here's a standard example of problems people have been asking me about. It's called like dictionary learning. So I have some matrix D, and I want to approximate it as the product of two lower dimensional matrices, okay? Or maybe with some regularizers, okay? And I'd like to solve that problem. Well, it's very attractive to do ADMM because each subproblem is convex, but it's not a convex problem. So like, but this is, engineers and machine learners really want to solve problems like this, okay? So that's another interesting thing, okay? And that's basically it. We're going to hear about things like that, and we're going to hear about many other things that have been done on the convex theory side as well, and let's get started.